In this next video, we're going to learn how to do stoichiometry when our reaction components are in the form of a solution. So what is a solution? A solution is a homogeneous mixture of two substances, which means that those two substances have to be mixed evenly. Remember the difference between homogeneous and heterogeneous mixtures from way back in chapter 1. So solutions have two components. They have the solvent, which is the component that is in solution in a greater amount, or the component that there is more of, and there's the solute, which is the component in the lesser amount, so the component there is less of. It's important to identify your solute and your solvent because it's going to be important when determining the molarity of a solution. So the molarity of the solution is described by the variable m, and capital M molarity is equal to the moles of solute over the liters of total solution. And in order to get those liters of total solution, that would, if it's not given to you, that would be the liters of solute plus the liters of the solvent. And again, that will give you your total solution volume. Sometimes it'll just be given to you in the problem. Other times you might have to solve it yourself. Solutions can be categorized as either concentrated or dilute. So what is the difference between these two? A concentrated solution has a large amount of solute, meaning it's going to have a high molarity. And a dilute solution is going to have a small amount of solute, which means it's going to have a low molarity. So there's not really an exact number that determines what is concentrated versus what is dilute. I like to say anything that is an order of magnitude above 1 molar is relatively concentrated. Anything that is less than 1 molar is relatively dilute. But again, there's still kind of some gray area, and it really depends on the type of chemistry that you're doing. So how do we use molarity in calculations? Let's do an example. What is the molarity of a solution containing 25.5 grams of KBr dissolved in enough water to make 1.75 liters of solution? So this is one of those examples that gives you the total liters of solution already, so you don't even have to calculate it. So we're solving for molarity, so it's asking us what is the molarity, which means that in our equation, molarity equals moles of solute over liters of solution. Now we're going to have to do some calculations to fill in some of these variables. One of them is already given to us. As you can see, we already have the liters of solution, so we can fill that in to the denominator where it says liters of solution. So we have molarity equals moles of solute over 1.75 liters of solution. Now we have to figure out the moles of solute. Our solute in this case is going to be our KBr. And the way that we can tell that is because it says that the KBr is dissolved in enough water. So the KBr is dissolved in water, meaning that the KBr is the solute, the water is the solvent. So the problem here is that we weren't given moles of solute, we were given grams of solute. But now we know how to do stoichiometry, so we can use those grams of solute to figure out the moles. So if we start with 2.5 grams of KBr, we can use the molar mass of KBr, which is 119.00 grams. And again, I always write the names of the entire chemical into the box. And that is the mass of 1 mole of KBr. We know that grams cancels with grams, and we're left with moles of KBr. And our answer, when you plug this directly into your calculator, is going to be 0.21429 moles of KBr. So clearly that is not the correct number of significant figures. Our correct number of significant figures is going to be 3, because the 25.5 has 3 sig figs. 119.00 has 5 sig figs. So since we're doing division, we want to round to 3 sig figs. So that's going to be these 3 values here. However, when I plug this into my main equation, I'm going to keep the 5 sig figs for now and then round to 3 at the very end. So now we know that the molarity, which is what we're solving for, is going to be equal to 0.214, and I'm going to underline that for our sig figs, 29 moles of KBr divided by 1.75 liters of solution. So you can pause the video for a moment to solve that on your calculator. And you should get, with the proper significant figures, that your answer is 0.122 molar. So that's how you find molarity. We can also use molarity in stoichiometry, as so. What is the minimum amount of 6.0 molar H2SO4 that is necessary to produce 25.0 grams of H2 gas according to the following reaction? Notice how I gave you the reaction here unbalanced, so your very first step is going to have to balance that. You are going to have to balance that reaction. So go ahead, pause the video, balance the reaction. And the correct coefficients for this newly balanced equation are 2, 3, 1, and 3. If you need a review on balancing chemical equations, you can go back to my previous video on how to do that. So we know that we have 6.0 molar H2SO4. So I'm going to label that here. And we know that we're trying to get to 25.0 grams of H2. We're trying to find the volume of H2SO4. So whenever we have molarity, like we have here, we're going to be using moles and volume of some sort. So even if we start with milliliters, we can always convert that to liters. So again, we're going to be using molarity and volume. So somehow we have to get from this 25 grams of H2 and figure out how we can get to that from this H2SO4. So what we're going to do is we're going to work backwards and do dimensional analysis. So we're going to start with 25.0 grams of H2. And we know we can't get directly from grams of H2 to any other substance, so the first thing we have to do is convert that to moles. The molar mass of H2 is 2.02 grams of H2 per 1 mole of H2. Now that we're in moles of H2, we can use the molar ratios from the coefficients of our balanced chemical equation. So for every 3 moles of H2, we also have 3 moles of H2SO4. Now we're in moles of H2SO4, and you would think that maybe we're a little bit stuck because, I don't know, I don't see moles of H2SO4 anywhere in this, anywhere given in this problem. So this is where it's really important to remember that molarity is equal to moles over liters. So notice how this is a unit that has that's made of a fraction. So whenever we have a unit that looks like a fraction, we can put that into our dimensional analysis. So if we want to put moles of H2SO4 on the bottom, we can use those molarity units and put liters of H2SO4 on the top. So what it means that we have 6.0 molar is that we have 6.0 moles of H2SO4 over 1 liter of H2SO4 solution. So we can fill that into our dimensional analysis, and then we can solve. So you can pause the video here to solve that equation. So once you've solved that, let's check. We can cancel grams with grams. We can cancel moles with moles. We can cancel moles of H2SO4 with moles of H2SO4. And we're left with liters of H2SO4. And notice how that matches what we were trying to find. We're trying to find the volume of H2SO4, and liters are a volume unit. If we want to make our math even easier, we can even cancel these 3's because we know that 3 divided by 3 is just 1. So when you solve this, you should get 2.06 liters. And then when we're taking into account significant figures, because we know this is a 3 significant figure number, this one also has 3 sig figs, and this number here has only 2 sig figs. All of the rest of them are exact numbers, and since they don't have any uncertainty, we don't include them when we're looking at significant figures. So here we're looking for a 2 sig fig answer, which means that our final answer should be 2.1 liters of H2SO4 solution.